Kia ora Year 12 and 13. In this video I'm going to find the general solutions for this third equation here. You can see that it's got double angles on the left hand side but looks reasonably okay on the right hand side. Now I'm going to show you the GeoGebra for this one before we do the question. So let's look at what we think the right hand side might look like. Well, 1 minus 4 sine squared x. Let's think about sine squared of x. Well, sine of x goes between 1 and negative 1. So sine squared of x is between 0 and 1. So that means that 1 minus 4 of that will go between which two numbers? Well, at the biggest it's going to be 1, and at the smallest it's going to be negative 3. So we can look at this over in GeoGebra and we can see that that red function there is 1 minus 4 sine squared x. And the left hand side is the green function, and that's a sum of a couple of trig functions. So you can see that the points we're looking for are here, here, and here. And it's kind of interesting. We're not going to explore this now, but just that you've got so much of those two graphs that are very, very close together. So that's quite cool. Right, but not needed for today. So going back to our question, what do we need to do to start with? Well, I'm going to substitute in some double angle identities and see what happens. So we've got sine of 2x plus 2 cos of 2x is equal to 1 minus 4 sine squared x. Sine of 2x has only one possible substitution, it's 2 sine x cos x. But for this one here, we've got a couple of choices. Looking over here at where I'm trying to link up to, I can see that I've got a sine squared in here. So I'm going to pick the version of cos 2x that's got sine squared in it. So it's going to be plus 2 times 1 minus 2 sine squared of x. If you'd chosen another one, you would get there, but you might just take a little bit more time to do it. So my equation now looks like this. Expanding out, we get 2 sine x cos x plus 2 minus 4 sine squared x is equal to 1 minus 4 sine squared x. So that's really nice because this and this simplify away. That leaves me with this thing here, which I'm going to put back to sine of 2x. I can hear some of you groaning down your laptops. So sine of 2x is equal to 1 take away 2, which is negative 1. So this is the first way that I'm going to do it. Right, now let's just draw our sine of x curve. Not sine of 2x, this is just the ordinary old sine of x. To find a general solution, we're going to say alpha is the angle whose sine is negative 1. So I'm looking for the number the calculator is going to give me is the one between negative pi and pi. So it's going to give me this one here, negative pi on 2. That's alpha. So now we're going to do general solutions on this. That means that 2x is equal to n pi plus negative 1 to the power of n times alpha, which is negative pi on 2. X is equal to n pi on 2 plus negative 1 to the power of n times negative pi on 4. So that's fine, or we could rewrite it more cleanly as minus negative 1 to the power of n times pi on 4. And if we chuck values into there, let's have a look at what comes out. We don't have to do this, right? So we've done our general solution, but it's worth just getting a feel for this because I'm going to do this a second way and we're going to see that it looks different, but it's going to come out with the same thing. So here's n and here's x. So we'll do, I don't know, negative 1, 0 and 1. Let's start with 0. What do we get? Well, we get 0 for this bit minus pi on 4. For n equals 1, we get pi on 2 plus pi on 4. So that gives me 3 pi on 4. This gives me negative pi on 4. For negative 1, we get negative pi on 2 minus a negative 1 to the power of negative 1. It's negative 1. So it's going to be plus pi on 4. So you can see that that is generating me the same value as that one. Now that will sometimes happen, it's quite cool when it does. It's just a thing not to be freaked out by. So that's doing it the first way. Let's look at a different way that we could have done this one. So this is the way that Ms. Young did it. She used a different switch over. So I'm going to go all the way back to, let's have a look. I'm going to go all the way back to the start and do it again. Now some of you watching, well, you probably will have stopped watching because you'll be saying, well, what's the point if we know how it's going to end up? So we had here 2 cos of 2x equals 1 minus 4 sine squared x. Now the expansion that she chose to do here was the cos squared minus the sine squared. I just want to check that I've got exactly the right equation before we start up again. 2 cos of 2x, yep, that's right. Okay, so this time what we'll do is we've got 2 sine x cos x plus 2 times cos squared x minus sine squared x is equal to 1 minus 4 sine squared x. Cleaning that up gives me 2 sine x cos x plus 2 cos squared x plus 2 sine squared x equals 1. So what can I see here? Well, I can see a cos squared plus a sine squared in here. So let's write it out like this. Cos squared x plus sine squared x plus another cos squared x plus another sine squared x. So that's this bit here. Plus 2 sine x cos x is equal to 1. Linking this up gives me 1 plus, now linking this up gives me cos x plus sine x squared. Right, so this is a really nice way to do it as well. You can split up this and see that this is a perfect square. That leads on to cos x plus sine x all squared is equal to 0. Which means that cos x equals negative sine x. Negative 1 is equal to sine x over cos x. In other words, tan x is equal to negative 1. So alpha here, we know this one, or we could use our special triangle, 1, 1, root 2. Alpha is equal to negative pi on 4. And we can go straight to our general solution for tan, which is x equals n pi minus pi on 4. And you'll see very easily that if you start plugging in values for n, you're going to generate exactly the same series of numbers that I did earlier. So let's see if I can find those numbers from the earlier question. Yep, up here. Right, so look at what came out when we did it the first way. We had negative pi on 4, then we had 3 pi on 4. And if we'd kept going, we would have found 7 pi on 4. But doing it this way, we got there with a tan general solution, but we get exactly the same thing. So both of those would get 4 marks. Let's go over to the GeoGebra and see how that works. So if you look at where I've done those circles, let's take off the black stuff, you can see that they are sitting at those multiples of, so here's the first one at negative pi on 4. And here's the next one, which is coming in at 3 pi on 4, and so on. So if you've got some good intuition for this developing, if you get a graph that looks like this and you can see that they're at periods of pi, then you should know that when you get down to a tan general solution and you're working, that you're going in the right direction. Okay, but there were 2 ways to get to this one. Just going over that one more time, because it's probably the first time we've seen that. Right, so we got there, Ms. Young's way gave us a tan general solution, and my way got us there using a sine general solution, but the values that they generate obviously have to be exactly the same ones. Okay, thanks for watching. I'll try and get through the rest of these this afternoon sometime.